Okay, so you know that feeling when you're scrolling through your phone and you come across something so absolutely insane that you have to stop and read it? Like your brain literally can't process what you're looking at because it violates everything you thought was possible. That's what happened to me 3 days ago, and I'm still not over it. 3 days ago, on November 3rd, 2025, astronomers were just doing their job, scanning the cosmos with their telescopes, looking for the usual stuff, supernovas, asteroids, whatever. And then something happened that made them freeze, completely stop what they were doing. One of them actually called another astronomer into the room and said, "You need to see this, right now." What they saw was the brightest cosmic explosion ever recorded in human history. Not just brighter than most explosions, not just a record, but something so extraordinarily, almost incomprehensibly bright that it shattered every single measurement they had from before. And the explosion was so bright, so insanely bright, that it reached the brightness of 10 trillion suns. Let that sink in for a second. 10 trillion suns, all burning at the same time, all in one explosion. Here's where it gets really wild though. This didn't just happen yesterday. It didn't happen last year. This explosion happened 10 billion years ago. 10 billion years. That's before Earth existed. That's before our sun even formed. That's so far back in time that when this star was being destroyed, the entire universe was a completely different place. Galaxies were still forming. Dinosaurs didn't exist yet. Life hadn't even figured out how to leave the oceans. The light from this explosion has been traveling through space for 10 billion years. It's been bouncing through the expanding universe, getting stretched out by the fabric of space itself, and it just arrived at our doorstep. We're just now seeing it. We're witnessing an ancient catastrophe that unfolded eons ago, and the cosmic messenger carrying that news is only just knocking on our door. But here's the absolutely crucial part. Here's why this matters so much that it's literally reshaping how scientists understand the universe. We're not just seeing a flash that happened in the past. We're watching an event that's still happening right now, or at least that's what it looks like from Earth. The explosion has been going on for 7 years straight. 7 years of continuous brightness. 7 years of this star being torn to pieces by a black hole so massive and so powerful that it's literally impossible to visualize. This black hole has a mass of 500 million suns. Not stars, suns. Let me say that again because I want you to really understand what we're talking about here. This black hole is 500 million times heavier than our entire sun. It's not a small thing in space. It's not just another black hole floating around. It's a cosmic monster. It's the kind of thing that shouldn't even exist according to early models of how black holes form. And yet there it is, lurking at the center of a galaxy 10 billion light years away. And somehow, some way, a star wandered too close to it. A massive star, not a tiny star like ours. A star that was probably 30 times bigger than our sun. A star that should have been strong enough to exist peacefully for billions of years. Instead, it got grabbed by gravity so powerful that nothing could escape, not even light, and that star got torn apart, completely destroyed, ripped to shreds in what astronomers call a tidal disruption event. The amount of energy released in that moment was so enormous that it's almost impossible to comprehend. The entire mass of our sun converted into pure energy through Einstein's equation. Every single atom of that sun transformed into pure radiation. All of that energy came pouring out in an explosion that reached the brightness of 10 trillion suns burning at the same time. When the Caltech team first saw the numbers, they didn't believe them. Matthew Graham, one of the lead astronomers, said they literally thought the instruments were making an error. They ran the calculations again. Different measurements, different approaches. Every single one came back with the same answer. This was real. This was actually happening somewhere out there in the cosmos. And this is what blew my mind when I first learned about this. We're not looking at something that happened and then faded away. This explosion started in 2018 when telescopes first detected it. Nobody realized what they were seeing at first. It looked like just another active galactic nucleus, a common phenomenon. But then something strange happened. Instead of getting dimmer like most cosmic events, it kept getting brighter. Month after month, year after year, it refused to fade. By the time astronomers realized something extraordinary was happening, the explosion had already increased in brightness by 40 times brighter than when they first spotted it. That's not a gradual change. That's not something that happens slowly. 40 times is the kind of increase that makes you sit down and really think about what you're witnessing. Now, you're probably wondering how an explosion from 10 billion years ago is still visible and still changing right now. That's where time gets really weird. That's where Einstein and gravity team up to create something that sounds like science fiction, but is actually real physics. And I'm going to explain exactly what's happening, because this is the moment where the universe stops making sense and starts making your head hurt in the best possible way. The black hole is so massive and so powerful that it literally warps time itself. The closer you get to it, the slower time moves. From the perspective of an observer far away from the black hole, time slows down to almost a stop. So when that star was being destroyed, from our perspective here on Earth, that event happened in a certain time frame. But the actual destruction, from the star's perspective, happened much faster. And because of how the universe works, those two different time frames are both absolutely correct. This means that what we're seeing right now, unfolding over 7 years, actually happened in just 2 years. We're watching the slowest motion replay of a cosmic catastrophe that you could possibly imagine. It's like someone put the most dramatic, violent event in the universe into ultra-slow motion so we could see every single detail of what happens when a star gets too close to a black hole and crosses a point of no return. And here's what happened on November 3rd, 2025. 7 years after this explosion started, after the light had been traveling through 10 billion light-years of expanding space, after it had been stretched and warped by gravity wells and colliding with cosmic dust and bouncing around the universe, that light finally reached Earth. And when it did, astronomers looked at it and realized they were witnessing something unprecedented, something that changes how we understand black holes, how we understand the early universe, and how we understand the limits of cosmic destruction. The question that probably just popped into your head is the same question that popped into mine. If this explosion was so bright, so absolutely insanely bright that it reached 10 trillion suns, what would happen if something like that occurred near us? What if a black hole this massive decided to tear apart a star in our galaxy? What would happen to Earth? Would we be vaporized from the radiation? Would the heat reach us even from billions of miles away? These are exactly the kinds of questions that keep astronomers up at night. And in this video, I'm going to answer every single one of them. I'm going to show you exactly what happened during those 7 brutal years. I'm going to explain how scientists actually discovered this event and how they figured out what was going on. I'm going to walk you through the 3 phases of a tidal disruption event so you can understand exactly how a star gets destroyed by a black hole. And I'm going to tell you whether we need to worry about this happening anywhere near our solar system. But before we get into any of that, you need to understand that this isn't just cool space trivia. This isn't just a random fact about the cosmos that's neat, but ultimately irrelevant to our lives. This discovery is fundamentally changing how we understand the universe. It's giving us information about the early cosmos that we couldn't get any other way. It's showing us that there are processes in the universe that are far more violent, far more destructive, and far more interesting than we ever imagined. And most importantly, it's a reminder that we're living in an era where we can actually see things that happened before Earth even existed. We can witness ancient cosmic events. We can study the universe as it was billions of years ago. And sometimes, if we're lucky and our telescopes are pointing in the right direction, we can catch something absolutely extraordinary happening right before our eyes. So let's jump into the story of how this discovery was made. Let's go back to 2018 to a team of astronomers at Palomar Observatory in California who were just doing routine observations of the cosmos. Let's see how they stumbled onto something so unusual that it took them years to figure out what they were actually looking at. Because the detective story behind this discovery is almost as interesting as the actual cosmic event itself. Back in 2018, the Zwicky Transient Facility, this amazing instrument that scans the entire sky looking for things that change, for things that appear and disappear and shift and transform, picked up something weird. There was this object called J22453743, and it was doing something unusual. It was there in the data, in the observations, but it wasn't acting like anything the astronomers had seen before. The Zwicky team, they're used to finding all sorts of things: supernovas, asteroid impacts, variable stars, things that flare up and fade away. But this was different. Matthew Graham and his team at Caltech started tracking this object more carefully. They noticed something that made them sit up and pay attention. The brightness wasn't just changing randomly. It was following a pattern that didn't match any known phenomenon. Most cosmic explosions reach their peak brightness and then gradually fade away. It's like a supernova. It gets really bright for a few months and then slowly dims over years. But J2245+3743 wasn't doing that. Instead, this object was getting progressively, relentlessly brighter. Over the course of months, it was increasing in brightness by massive factors, and it wasn't stopping. Month after month, the brightness just kept climbing. The team ran the numbers, they checked their instruments, they looked at the data from different telescopes. Everything confirmed the same thing. Whatever was out there at J2245+3743 was getting more and more luminous, and nobody could quite figure out why. By 2019, the brightness had increased by enormous factors from when they first detected it. By 2020, it was even brighter. By 2021, 2022, 2023, the trend continued. Year after year, this object kept gaining in luminosity. It's like someone turned up the brightness dial on a cosmic lamp and just kept turning it higher and higher with no end in sight. The scientific community started taking notice. This wasn't just another blip on the cosmic radar. This was something genuinely strange and genuinely important. And then in November 2025, after years of observations, after collecting data from multiple telescopes, after running thousands of calculations and models and simulations, the measurements came in. The brightness had reached a level that nobody had ever recorded before. 10 trillion times the brightness of our sun. 10 trillion. That's a 1 followed by 12 zeros. That's a number so large that if you tried to count to it, counting one number per second, it would take you over 300,000 years. When those measurements confirmed what the data was suggesting, the astronomical community essentially stopped what they were doing. Papers were written, emails were sent out across the world. Astronomers who didn't normally work together started collaborating because what they were looking at was a puzzle piece that didn't fit anywhere in the current understanding of how the universe works. And that's when people started asking the really important question: what the hell is actually going on out there? The answer to that question required understanding something about black holes that most people don't think about. It required understanding what happens when a star gets too close to the most dangerous object in the universe. And it required understanding that the universe has ways of destroying things that are far more violent, far more dramatic, and far more spectacular than anything we typically imagine when we think about cosmic destruction. Let me take you back to that moment, November 2025. The measurements are coming in. The data is confirming what everyone was starting to suspect. This wasn't just unusual. This was unprecedented. This was the kind of discovery that only happens a handful of times in a generation, if you're lucky. The global astronomical community was buzzing. Everyone was trying to figure out the same thing. What could possibly cause something 10 billion light-years away to shine brighter than anything we'd ever recorded? Before the answer came together, there was this period of intense confusion. Scientists were throwing theories at the wall to see what would stick. Some suggested it was a new type of quasar, but the brightness curve didn't match. Some thought maybe it was something we'd never seen before, some entirely new cosmic phenomenon. Papers were being written in real time. Emails were flying back and forth between observatories. Everyone wanted a piece of this mystery. Everyone wanted to be the one to figure out what J2245 plus 3743 actually was. Matthew Graham held a meeting with his team. They spread out all the data they'd collected since 2018, 7 years of observations, thousands of data points, each one telling them something different, something crucial about what was happening. They looked at the light spectrum, they analyzed the infrared radiation, they checked the ultraviolet emissions. Every piece of information pointed toward the same impossible conclusion. One of the researchers, I'm imagining her sitting there at the table, probably caffeinated beyond reason at this point, suddenly stopped talking, stopped moving, just stared at the screen. And then she said something that changed everything. She said, "This looks like a tidal disruption event." The room went quiet, because everyone in that room knew exactly what that meant. A tidal disruption event. A star getting torn apart by a black hole. For those of you who don't know, a tidal disruption event is one of the most violent things that can happen in space. It's what occurs when a star gets too close to a black hole and gravity becomes so uneven across the star's surface that it literally rips the star into shreds. Imagine stretching a piece of gum. Now imagine doing it from both ends with infinite force. That's kind of what happens to a star. The side of the star facing the black hole gets pulled incredibly hard, the far side gets pulled less hard, and the star just comes apart. But here's the thing about tidal disruption events that made everyone in that room pause. They're rare, extremely rare. In a typical galaxy, a tidal disruption event might happen once every 100,000 years or so, maybe even less frequently than that. So the odds of us actually witnessing one, of our telescopes being pointed in the right direction at the right time, looking back into the early universe and catching one of these events still in progress, those odds are astronomical. And I mean that literally. Yet that's exactly what seemed to be happening. Every analysis they ran brought them back to the same conclusion. A massive star had gotten too close to a supermassive black hole. The black hole had grabbed it, and then, over a period of time, the star had been torn apart and converted into radiation that was now reaching Earth. The brightness we were seeing, the 10 trillion sun equivalent, that was the energy from a star being destroyed. Now, when Graham told the broader astronomical community what they'd found, the response was enormous. But there was also skepticism, because this particular tidal disruption event had some characteristics that didn't quite match anything in the literature. It was brighter than expected. It had been increasing in brightness for much longer than expected. The timeline didn't match previous observations. It was like finding a jigsaw puzzle piece that looked like it should fit, but it was just slightly the wrong shape. So instead of accepting the conclusion immediately, the astronomical community did what science does best. They started asking harder questions. They demanded more observations. They wanted multiple telescopes looking at this thing to confirm what was being claimed. The Zwicky Transient Facility had made the initial discovery, but now Caltech and other institutions were bringing in their heavy instruments. The Palomar Observatory was doing detailed observations. Other telescopes around the world were pointing at J2245 plus 3743 to collect their own data, and everything confirmed it. This was real. This was genuine. This was a tidal disruption event unlike anything astronomers had documented before. The scientific papers started being written. Preliminary findings were submitted to journals. Preprints were posted online so other scientists could review the work immediately without waiting for traditional peer review processes. And slowly, the astronomical community came to accept what their data was telling them. But to really understand what happened to this star, you need to understand the 3 essential facts about black holes that make tidal disruption events possible. And I'm going to give these to you quickly because they're crucial to understanding the rest of the story. And I don't want to bury you in technical details. I want you to get what's actually happening here. Fact number 1 is the most important one. Black holes are gravitational monsters. They're regions of space where gravity has become so intense, so overwhelming, that it creates something we call an event horizon. This is a boundary, an invisible line around the black hole. Cross that line and you can't escape. Light can't escape. Radiation can't escape. Nothing can escape. Whatever gets past that event horizon is gone forever. The gravity near a black hole is so strong that the closer you get to it, the more gravity increases. And not just a little. The increase is dramatic, exponential, crushing. Fact number 2 is about mass and density. The black hole in this story, the one that destroyed J2245, 3743's star, it has a mass of 500 million suns. That means if you took 500 million of our entire suns, with all their nuclear fusion, and all their mass, and all their gravitational pull, and you compress them down into a single point, that's roughly equivalent to the mass of this black hole. But here's the thing that makes it actually dangerous. That entire mass isn't spread out across space like a normal star. It's compressed down to a relatively small area. The density is absolutely insane, and that compressed mass creates gravity that's beyond comprehension. Fact number 3 is about distance and gravity gradients. This is the most important fact for understanding what happened to the star. Gravity decreases with distance. So if you have an object with uneven gravity pulling on it, one side closer to the source getting pulled much harder than the other side, the object gets stretched. The closer side experiences stronger gravitational acceleration. The farther side experiences weaker gravitational acceleration. And the difference between them is what creates tension. Enough tension and you can stretch something apart. Now combine all 3 of these facts. You have a black hole with the mass of 500 million suns compressed to an incredibly dense point. You have gravity that increases exponentially as you get closer to it. And you have this effect where one side of an object gets pulled much harder than the other side. Put a star near this black hole, a star that's 30 times the mass of our sun, a star that's massive and strong and should be able to withstand almost anything. And what happens? The gravity from the black hole starts pulling on the star. The closer side of the star experiences stronger gravity. The farther side experiences weaker gravity. And the difference between these 2 gravitational forces creates this stretching effect. As the star gets closer and closer to the black hole, this stretching effect becomes more and more intense. The gravity gradient becomes more extreme. And eventually the stretching force becomes so strong that it exceeds the internal structural strength of the star. The star can't hold itself together anymore. It starts to come apart. But this process, this stretching and tearing apart of the star, it doesn't happen instantly. It happens gradually. There's a moment when the star first gets too close, when the stretching effect first becomes significant. There's a moment when the star starts to tear, and there's a moment when the star is completely destroyed, when it's been reduced to thin streams of material spiraling into the black hole. And between those moments, there's a period of time during which the star is being transformed from a massive cosmic object into hot material being consumed by gravity. The question everyone was asking in November 2025 was this: what were we actually seeing? Were we seeing the moment when the star first got torn apart? Were we seeing the moment of maximum brightness when the most material was being consumed? Were we seeing the tail end of the event when most of the star had already been destroyed? The answer to that question would tell them a lot about what was actually happening. And this is where the timeline became crucial. The explosion we now know started in 2018. That's when telescopes first detected the flare. But in 2018, it wasn't nearly as bright as it would become. It was just starting. The event had just begun. And then for 7 years, year after year, the brightness kept increasing. This told astronomers something profound. They weren't seeing a moment in time. They were seeing an extended process. They were watching a star being torn apart in slow motion over a 7-year period. Which sounds impossible, but I'm going to explain exactly why it's happening in just a moment, because that's where time gets genuinely weird. But first, let me tell you about the black hole that did this. Because knowing about this black hole is essential to understanding the scale of destruction we're talking about. The black hole is called the central supermassive black hole in the J2245 galaxy. It lives at the center of a galaxy roughly 10 billion light-years away. 10 billion light-years is such a vast distance that it's honestly hard to conceptualize. Light, the fastest thing in the universe, takes 10 billion years to travel from that galaxy to Earth. In human terms, 10 billion years is longer than the current age of the universe. No, wait, that's not right. The universe is about 13.8 billion years old. So this galaxy is from a time when the universe was only about 3.8 billion years old. That was before Earth existed. That was before our sun formed. That was back when the universe was young, when galaxies were still figuring out how to exist. And in that galaxy, at its center, this monster black hole was just sitting there. It had been sitting there for who knows how long. And then, at some point before 2018, a star in that galaxy got too close. Maybe the star was orbiting nearby, and its orbit degraded over time. Maybe it got knocked out of its regular path by some collision or gravitational interaction. Maybe it was just incredibly unlucky and happened to wander into the danger zone. However it happened, the star crossed the point of no return. Once it crossed that point, gravity took over. The star got pulled inward. The tidal forces started to act on it. And for the next several years, this star was being stretched, heated, and torn to pieces. And the radiation from this process, the light and energy released as the star was destroyed, that radiation started traveling through space. It had to journey 10 billion light-years. It had to pass through expanding space, getting redshifted and stretched by the cosmic expansion. And finally, in 2018, the leading edge of that light reached our solar system and started being detected by our instruments. From the moment we first detected it in 2018 to the moment in 2025 when the peak of that emission reached Earth, we were seeing different parts of the same event. The brightness was increasing because we were receiving the radiation from deeper and deeper into the star's destruction. And the reason it took 7 years to reach maximum brightness instead of just a few months is because of how time works near a black hole. And that, my friends, is where this story gets genuinely mind-bending. That's where we're about to enter territory that sounds like it came from a science fiction novel, but is actually just Einstein's theory of relativity, working in one of the most extreme environments in the universe. So here's the thing about time that most people don't really think about. We treat time as this constant thing, right? We assume that everywhere in the universe, time passes at the same rate. A second is a second is a second. If I sit at my kitchen table and time passes, and you sit on a spaceship traveling at the speed of light, we both experience the same amount of time passing. That's just intuitive. That's how it feels. But Einstein basically said, nope, that's wrong. And he was right. Time doesn't work that way. Time is affected by gravity. Time is affected by motion. And the closer you get to a source of intense gravity, like a black hole, the slower time moves. And I don't mean that in some poetic sense. I mean it literally, measurably, objectively. Time actually passes more slowly. Imagine you have two observers. Observer A is sitting far away from any massive objects. Observer B is sitting right next to a black hole. Both of them are looking at their watches. Both of them are experiencing their own personal time moving at what feels like normal speed to them. But if Observer A looks at Observer B's watch from far away, it's going to look like it's running slow. Time on Observer B's watch will appear to be ticking much more slowly than time on Observer A's watch. This is one of the predictions from Einstein's general relativity that we've actually proven multiple times in experiments. It's not theoretical anymore, it's reality. Atomic clocks on airplanes run slightly slower than atomic clocks on the ground. Atomic clocks at the top of mountains run slightly faster than atomic clocks at sea level. The differences are tiny, measurable in microseconds, but they're real. Gravity affects time. It's just a law of physics. Now take that principle and dial it up to extreme levels. Put it near a black hole where gravity is not just strong, but almost incomprehensibly strong. And suddenly time doesn't just run a little slower, it runs dramatically, noticeably slower. If you're near a black hole and someone far away watches you, they'll see you moving in what looks like slow motion. Your biological processes slow down, your heartbeat slows down, your thoughts slow down, everything slows down. But here's where it gets really weird. From your perspective, if you're the one near the black hole, everything is normal. Your heartbeat feels normal, time feels normal. It's only when you compare yourself to someone far away that you realize something strange is happening. You're aging slower, your watch is running slower, but from your point of view, everything is ticking along at the normal rate. This phenomenon is called time dilation, and it's one of the most mind-bending consequences of general relativity, and it turns out to be absolutely crucial to understanding what we're seeing with J2245 plus 3743, because the star that got torn apart didn't experience 7 years of destruction. From the star's perspective, the whole process probably took maybe 2 years, but from our perspective here on Earth, watching that star from 10 billion light-years away, we're seeing the event unfold over 7 years. Let me explain how that works. When the star first started getting pulled into the black hole's gravity well, it was moving faster and faster. As it fell deeper into the black hole's gravitational field, It was experiencing extreme time dilation. From the star's perspective, time was passing normally. But from our perspective, time on that star was running incredibly slowly. It's like watching a film in ultra-slow motion. The process of the star being torn apart involves several stages. There's the initial approach when gravity starts getting intense, but the star is still intact. There's the stretching phase when the tidal forces are literally pulling on the star. There's the moment when the star loses structural integrity and starts to come apart. And there's the final phase when the star is being ripped into streams of material that spiral toward the black hole. All of this happens from the star's frame of reference relatively quickly. But from our frame of reference, all of it unfolds very slowly. So when we see this explosion increasing in brightness over 7 years, what we're actually seeing is the light from different stages of that destruction reaching Earth at different times. We're seeing the radiation from the early stages first. Then, months and years later, we're seeing the radiation from progressively later stages of the destruction. The brightness is increasing not because the explosion is getting more violent, but because we're receiving the radiation from progressively deeper into the process. The peak brightness, the moment when the entire J2245 explosion reached its maximum brilliance, that moment corresponds to the time when the most material was being consumed by the black hole simultaneously, when the most energy was being released. And that peak reached Earth on November 3rd, 2025, 7 years after the light from the early stages of the destruction had first reached us. 7 years of watching a cosmic catastrophe unfold in slow motion. Now, you might be wondering, how do we actually know all this? How do we know it's not just speculation? How do we know the star was actually torn apart and not something else? The answer is in the light itself. When something gets incredibly hot, it releases radiation. That radiation has a specific spectrum. It has certain wavelengths that are characteristic of different temperatures and compositions. Astronomers can look at the spectrum of light coming from J2245 and figure out what's happening. When a star is being torn apart by a black hole, the material gets heated to billions of degrees. At those temperatures, you get this incredibly bright X-ray emission. The spectrum shows the distinctive fingerprints of elements being heated to extreme temperatures. Carbon, nitrogen, oxygen, all the elements that made up the star. They're being exposed to radiation and heat that tears them apart at the atomic level. The spectrum that astronomers saw from J2245 plus 3743 was exactly what you'd expect to see from a tidal disruption event. It was the smoking gun. But there's another piece of evidence that made it clear this was really happening. The way the brightness changed over time followed a very specific mathematical pattern. For tidal disruption events, there's a predicted relationship between how long the event lasts and how bright it gets, and how much the brightness changes. It's called the light curve. And when astronomers plotted the light curve for J2245 plus 3743, it matched the theoretical predictions almost perfectly. It was like the universe was saying, yep, that's exactly what you thought was happening. And then there was the fact that the brightness kept increasing far longer than it should have for most cosmic phenomena. Most supernovas reach maximum brightness and then fade away within months or a year or two at most. But J2245 plus 3743 kept getting brighter for years and years. It was like the universe was feeding material into this explosion in a controlled way, slowly but steadily pumping more and more energy into it, which makes perfect sense if what's happening is a star being slowly torn apart and gradually consumed by a black hole. So by November 2025, the astronomical community was fully convinced this was a tidal disruption event. This was a star being destroyed, and we were witnessing it in real time, or at least what passed for real time when you're observing something 10 billion light years away and dealing with all the relativistic effects that come with that distance. But here's the part that really gets people. When this star was being torn apart, Earth didn't exist yet. Humanity didn't exist yet. The dinosaurs hadn't evolved. Life was probably barely making it on Earth, if it even existed at all. The light from this destruction was already halfway to Earth when the first humans walked on the African savanna. It had been traveling through space for another billion years while humans evolved and built civilizations and went to the moon and invented the internet. And only now, in November 2025, has that light finally arrived and is telling us about something that happened in an ancient, distant past. It's a reminder of the vast timescales involved in astronomy. It's a reminder that when you look at the stars, you're looking at the past. Every star you see in the night sky, the light from that star took some amount of time to reach you. For nearby stars, that's years or decades. For distant galaxies, that's millions or billions of years. So when you're looking at a distant galaxy, you're literally looking at what that galaxy looked like in the past. You're a time traveler of sorts. You're receiving information from ancient history, written in light. And in the case of J2245 plus 3743, we're receiving information about an event so violent, so destructive, so utterly catastrophic that it reshaped the universe around that black hole. That star is gone now, completely gone. What remains is a disk of hot material spiraling into the black hole. Some of that material has already crossed the event horizon and is forever lost to the rest of the universe. But before it crossed that point of no return, it released energy equivalent to the entire mass of our sun, converted to pure radiation, through Einstein's E=mc² equation. That's an almost unimaginable amount of energy. If you could somehow capture all the energy that our sun will release over its entire 10 billion year lifespan, and you condensed it down and released it all at once, you'd get something on the order of what we saw from J2245 plus 3743. Except J2245 plus 3743 did it in a matter of years, and the brightness was so intense that even traveling across 10 billion light-years and getting dimmed by the expansion of space, even after all that, the light that reached Earth was bright enough to be detected by our telescopes and recorded in our data. Now, this is important because it tells us something fundamental about what happens when stars get too close to black holes. It tells us that the destruction is not just a quick event, it's a process that unfolds over time. There are phases, there are stages, and each stage releases different amounts of energy and produces different types of radiation. Understanding those stages, understanding what happens at each phase, that's crucial to understanding the full picture of what happened to this star. So let me walk you through what actually happened during those 7 brutal years of observation. Let me show you the 3 phases of destruction that turned a massive star into nothing but radiation and memory, because this is where the real horror of a tidal disruption event becomes clear. This is where you see what gravity can do when it's unleashed in its most extreme form. The destruction of a star by a black hole unfolds in distinct phases. Each one is more violent than the last. Each one brings us closer to the moment of maximum horror, and each one tells us something crucial about what we're witnessing when we look at J2245 plus 3743. Phase 1 is what we call the spaghettification phase. I know that sounds ridiculous. Spaghettification. It sounds like something out of a cartoon, but it's the actual term that astronomers use, and once you understand what it means, you'll realize it's actually the most accurate name for what happens. During this phase, the star is approaching the black hole. It hasn't reached the event horizon yet. It's still light years away, relatively speaking, but gravity is already having an effect. Imagine the star as a sphere. It's got mass distributed throughout it. It's got a center, and it's got an outer surface. Now imagine that this sphere is falling toward the black hole. The side of the sphere that's closest to the black hole experiences gravitational acceleration that's way more intense than the side that's farther away. And the difference between these two gravitational forces starts to stretch the star. The material on the near side gets pulled harder. The material on the far side gets pulled less hard. And the star, which has been holding itself together against its own gravity for billions of years, suddenly finds itself being pulled in opposite directions by an external force so powerful that it can't resist. The star starts to stretch. It starts to deform. It goes from being roughly spherical to being more and more elongated. If you could somehow watch this process happening in real time, the star would look like it was being taffy pulled in opposite directions. The near side would start bulging out toward the black hole. The far side would start bulging out away from the black hole, and the star would become increasingly stretched and distorted. The pressure building up inside the star as it's being pulled apart becomes enormous. But the thing about a star is that it's massive. It's got a lot of internal pressure holding it together. The core of the star is held up by the weight of all the material above it. The pressure and temperature in the core are so extreme that they create an outward pressure that balances the inward pressure from gravity. The star is in equilibrium. But once the tidal forces start acting on it, once gravity from the black hole starts pulling on different parts of the star with different intensities, that equilibrium breaks down. During this phase, as the star is being stretched, the material inside it starts to heat up. You're essentially pulling a huge object apart. When you do work on an object, when you exert a force over a distance, you transfer energy to it. That energy has to go somewhere. In this case, it's being converted to heat. The star gets hotter, the temperature inside increases, and as the temperature increases, the pressure increases. This is happening gradually over the course of months or years from our perspective, but it's still happening. The star is being warmed by tidal heating, just from being pulled on by the black hole's gravity. The material inside starts to ionize. You've got atoms breaking down into electrons and nuclei. You've got the outer layers of the star starting to expand and puff outward as the pressure inside increases. And then something crucial happens. The star gets close enough to the black hole that the tidal forces exceed the internal strength of the star. The gravity gradient becomes so extreme that the star can no longer hold itself together. This happens at what's called the tidal radius. Cross that boundary and the star is doomed. The internal pressure can't overcome the external tidal forces anymore. The star starts to come apart. The first signs of this are subtle. Maybe a bulge appears on the surface. Maybe some material starts to come loose from the surface layers, but then it accelerates. and within a relatively short time frame, the star transitions from being stretched to being actively disrupted. The outer layers start to strip away. Material gets pulled off the surface of the star and starts to accelerate toward the black hole. The star is no longer just being stretched, it's being torn to pieces. This transition from phase 1 to phase 2 happens fairly quickly once the tidal radius is crossed. For our star, this probably happened over a period of weeks or months. But from our perspective on Earth, watching through the relativistic time dilation effect, this transition happened over a longer period of time. We start to see the light from the star becoming brighter, not dramatically yet, just gradually increasing. The energy being released starts to increase as more and more material comes loose from the star. Phase 2 is what we call the accretion phase, or sometimes the super-Eddington phase. This is when the star has been shattered into fragments and streams of material that are now spiraling into the black hole. At the beginning of this phase, you have pieces of the original star falling into the black hole at different rates. Some pieces have more angular momentum than others. Some are moving faster, some are moving slower, and they're all starting to collide with each other and heat up. As these streams of material fall inward, they're getting squeezed and compressed by gravity. The density increases, the temperature increases dramatically. We're talking billions of degrees now, hotter than the core of any star, hotter than the temperature inside a nuclear weapon. The material is so hot that it's producing radiation across the entire electromagnetic spectrum. Visible light, ultraviolet radiation, X-rays, gamma rays, all of it. This is where the brightness really starts to increase. This is where an observer on Earth starts to see the explosion getting noticeably brighter. The radiation from the superheated material is pouring out into space. It's spreading outward in all directions, and some of it is pointed at Earth. Some of that radiation is making the journey across 10 billion light-years and being detected by our telescopes. The efficiency of energy conversion during this phase is brutal. When material falls into a black hole, it releases an enormous amount of energy before it crosses the event horizon. The precise amount depends on several factors, including how close the material gets to the black hole before falling in. But you're looking at converting a significant fraction of the rest mass into energy. We're talking about tens of % of the material's mass being converted to pure radiation. Compare that to nuclear fusion, which only converts about 0.7% of the mass into energy, or chemical reactions, which convert even smaller amounts. The energy released from matter falling into a black hole is vastly more efficient. And in this case, we're talking about millions upon millions of tons of material from the destroyed star falling into the black hole. All of that mass is being converted to radiation. All of that energy is pouring out. During this phase, the brightness increases dramatically. We're not talking about gradual increases anymore. We're talking about increases by factors of 5, 10, 20 or more. The explosion is getting exponentially brighter as more and more material is being consumed. The radiation from different pieces of stellar material that are all falling into the black hole and colliding with each other is piling up. The energy density increases, the brightness increases. And it's during this phase that we see the most dramatic features in the light curve. This is when an observer on Earth would see the explosion going through its most violent transformations. The brightness is changing rapidly. The spectrum is changing. New features appear in the data. This is the crescendo. This is the building up of energy and heat and violence. Phase 2 lasts for a considerable amount of time because there's so much material to consume. We're talking about the mass of a star here, which is enormous. Even if the black hole is eating it at an incredible rate, it still takes time. From the star's perspective, this phase might last months or even a year or two. But from our perspective, with the relativistic time dilation effect included, phase 2 extends over several years. This is the multi-year period during which the brightness is continuously increasing. And then we reach phase 3, the final phase, the moment of maximum power, the moment when all the energy that's going to be released reaches its peak. Phase 3 is the climax. It's the moment when the most material is being consumed simultaneously. It's the moment when the energy release rate hits its maximum, and it's during phase 3 that the explosion reaches its absolutely maximum brightness. By November 2025, we were seeing the peak of phase 3. The light from the moment of maximum brightness in the destruction of this star had finally reached Earth, and the measurements showed that the brightness had reached 10 trillion suns. Let me emphasize that one more time. The explosion was as bright as 10 trillion of our suns, all burning at their full power simultaneously, all in one explosion, all at one location. To give you a sense of scale, the entire Milky Way galaxy, with all its hundreds of billions of stars, is estimated to have a total luminosity of about 10 to 20 billion solar luminosities. The peak brightness of J2245+3743 was 500 to 1,000 times brighter than the entire Milky Way galaxy. We're talking about an explosion so bright that if it were as far away as the Andromeda galaxy is from us, which is only 2.5 million light-years away, it would appear brighter than the full moon in our sky. It would be blindingly bright. You would see it in daylight. You would see it during the day. It would completely wash out every other feature in the sky. And this is coming from something that's 10 billion light-years away. 10 billion light-years away, and it's still bright enough to be detected by our telescopes and recorded in our data and analyzed and published and studied. The amount of energy involved is almost incomprehensible. If you could somehow capture all of that energy, all of that radiation that was released during the peak of the explosion, and you could harness it, you could power human civilization for an inconceivable length of time. During phase 3, the radiation being emitted is in the high energy range. We're talking X-rays and gamma rays primarily. The visible light component is there, but it's a small part of the total energy output. Most of the energy is in forms of radiation that we can only detect with specialized instruments. Satellites above Earth's atmosphere that are sensitive to X-rays and ultraviolet radiation. Ground-based observatories that look at the visible and infrared light. Radio telescopes that detect any radio emission. All of these instruments were gathering data on J2245 plus 3743 during this peak period. And what the data showed was remarkable. The spectrum of the radiation showed signatures of an extremely hot accretion disk. You had material at temperatures of tens of millions of degrees being ionized and heated by the intense radiation environment created by the black hole. You had the signatures of elements like hydrogen, helium, carbon, nitrogen, oxygen, all the elements that made up the star, now existing as individual atoms or ions being stripped by radiation. The brightness peaked in November 2025. That was the moment when the maximum amount of material was being consumed by the black hole. That was the moment when the energy release rate was at its absolute highest. After that peak, the brightness started to decline, not dramatically. We wouldn't see dramatic dimming in the short term, but the peak had been reached. The explosion had reached its maximum power. After that, it would be a gradually decreasing process as the remaining material spiraled into the black hole and was consumed over a longer timescale. From the perspective of astronomers here on Earth, this peak in November 2025 represented something extraordinary. It was a moment of achievement for their field. They had discovered an event so rare and so extreme that it offered insights into physics at its most fundamental levels. They had captured data on a process that we could otherwise only study theoretically. They had witnessed destruction on a cosmic scale that demonstrated the power of gravity in its most extreme manifestation. But for that star, somewhere out there in space 10 billion light-years away, the peak brightness represented something entirely different. It represented the moment of its final destruction, the moment when the last of its material was being torn apart and consumed, the moment when 30 solar masses worth of material that had been stable and coherent was being transformed into radiation and scattered across the universe. The star was gone, completely gone. What remained was only the radiation being released, carrying the information about the star's destruction outward into space. And then, after that peak in November 2025, the brightness starts to decline. The explosion is entering its final stages. The star, what's left of it, has been completely consumed. The spectacular destruction has happened. What remains is just the gradual dimming as the last traces of stellar material fall into the black hole and disappear beyond the event horizon. The most violent chapter is over. The cosmic drama that started 7 years before reaching us is starting to wind down. In a few more years, the brightness will have diminished to the point where it becomes harder to observe. The explosion will fade into the background of cosmic phenomena, and eventually J2245 plus 3743 will return to being a relatively normal, active galactic nucleus, a black hole still consuming material, still radiating energy, but no longer producing anything extraordinary. But here's what's remarkable about all of this. Here's what really gets under your skin when you think about it. Every single moment of this process that we observed, every increase in brightness, every change in the spectrum, every piece of data that came back from our telescopes, all of it was information about something that had already happened. We were essentially reading the fossil record of a cosmic catastrophe. The actual destruction had concluded years ago. The peak brightness we measured in November 2025 corresponded to an event that, in the rest frame of the black hole and the star, had already finished playing out. We're living in the afterglow. We're seeing the echoes. We're receiving messages from the ancient past written in light. And that's genuinely profound if you take a moment to think about it. Somewhere out there's a black hole surrounded by a thin disk of hot material, the accretion disk. Most of the star is gone. Most of it has fallen past the event horizon and is lost forever. But some of it, some fraction of the material, is still spiraling inward, still being heated, still releasing radiation, and that radiation will continue to reach Earth for years to come, gradually dimming as the star's remnants are fully consumed. Now you might be thinking, okay, so we saw something really bright in space. We figured out what caused it. Great. But what does this actually tell us? Why should anyone care? And that's a fair question. So let me put this in perspective for you. Let me show you how extraordinary this event actually is by comparing it to other cosmic explosions and catastrophes that we've already studied and documented. Start with supernovas. A supernova is when a star explodes. Usually it's a massive star that's reaching the end of its life. It runs out of fuel in its core. The core collapses. The outer layers come crashing down inward. And then there's this rebound. The material bounces off the core and explodes outward. It's incredibly powerful. The explosion can outshine an entire galaxy of billions of stars, at least temporarily. A typical supernova, a Type II supernova, can reach peak brightness of about 1 to 10 billion solar luminosities. J2245+3743 reached 10 trillion solar luminosities. That's 1,000 to 10,000 times brighter than a typical supernova. And it's not like supernovas are rare events. We see them all the time. In any given galaxy, you might expect to see a supernova every century or so. They're one of the most energetic events in the universe. But they're still significantly dimmer than what we saw with J2245+3743. Then you've got quasars. These are incredibly bright objects at the centers of distant galaxies. A quasar can produce thousands of solar luminosities just as a baseline level of luminosity. Some of the brightest quasars can reach millions or even billions of solar luminosities. They're powered by black holes that are actively consuming material. In many ways, a quasar is what you get when a black hole is fed a steady diet of material. It's constantly radiating energy as that material spirals inward and gets consumed. But even the brightest quasars usually top out at around 100 billion solar luminosities or so. J2245+3743 exceeded that by a factor of 100. 10 trillion versus 100 billion. The explosion we're talking about was hundreds of times brighter than the brightest known quasars. There are also gamma-ray bursts. These are among the most energetic phenomena known to astronomy. A gamma-ray burst is an incredibly bright flash of gamma radiation that lasts anywhere from a fraction of a second to a few minutes. During a typical gamma-ray burst, an enormous amount of energy is released in a very short time. The peak brightness can rival or even exceed that of the brightest supernovas. But a gamma-ray burst is over relatively quickly. It flashes and it fades. The energy gets released in a burst. J2245+3743 was different. It wasn't a burst. It was an extended event that lasted years. It wasn't a sudden flash. It was a gradually increasing and then gradually decreasing phenomenon. It released its energy over an extended timescale. And in terms of total energy output, when you integrate the brightness over the entire 7 years, the total energy released was staggering. And here's the most interesting comparison. There have been other tidal disruption events documented. We've seen stars torn apart by black holes before, but this one was different. The black hole was more massive. The star was larger, the distance was greater, and the peak brightness was higher than any previously recorded tidal disruption event. It was, as far as we can tell, the most luminous tidal disruption event in recorded history, the brightest cosmic flare ever detected by humanity. In other words, we got incredibly lucky. The odds of catching one of these events at all are low. The odds of catching one that's this bright, this extreme, this unprecedented, those odds are even lower. But we caught it. We had our telescopes pointed in the right direction. We had the instruments sensitive enough to detect it. We had the expertise to recognize what we were seeing and to understand what was happening. In some sense, the universe gave us a gift. It gave us a front row seat to one of the most violent, most catastrophic processes imaginable. But that leads to the question that everyone was asking once the measurements came in. If this happens 10 billion light years away, what would happen if it happened close to us? What if there was a black hole in our neighborhood and a star got too close to it and we got to witness a tidal disruption event from up close? Let's think about this. Our galaxy, the Milky Way, has a supermassive black hole at its center. We call it Sagittarius A star, or SGR-A class. It's the most massive single object in our galaxy. Its mass is about 4 million times the mass of our Sun. Compared to the black hole in J2245+3743, which is 500 million times the mass of our Sun, Sagittarius A star is relatively modest. It's a heavyweight, but not in the same league. But let's imagine that somehow, a massive star wandered too close to Sagittarius A star. Let's imagine that tidal disruption event unfolding in our own galaxy. What would happen to Earth? First, let's consider the distance. Sagittarius A star is located at the center of the Milky Way, which is about 26,000 light-years away from us. That's an enormous distance, but it's not incomprehensibly far compared to intergalactic distances. If a star got torn apart by Sagittarius A star, and produced an explosion as bright as J2245+3743, what would we see from Earth? Well, first of all, we'd definitely see it. The brightness reaching Earth would be extraordinary. If J2245+3743 happened at the distance of Sagittarius A star, instead of at 10 billion light-years away, the brightness would increase by a factor proportional to the inverse square of the distance ratio. The math works out to mean that an explosion at the center of the Milky Way with the same intrinsic brightness as J2245+3743 would reach Earth at about 1 million times brighter than it currently does. That's bright enough that it would probably appear as an extremely bright spot in the sky during the daytime. It would probably outshine the full moon at night. If it were happening during the night, it would cast shadows on the ground. You could read a book by the light from it. The entire night sky would be transformed into something alien and unrecognizable. But that's just the light and radiation that reaches Earth as electromagnetic energy. That's the visible and invisible light that travels in straight lines through space and arrives at our planet. The radiation from that explosion would include X-rays and ultraviolet light and other high-energy particles. These would hit Earth's atmosphere. The upper atmosphere would absorb a lot of this radiation, but some of it would likely penetrate deeper. A pulse of X-rays reaching Earth's upper atmosphere would cause ionization. It would create a surge of charged particles. It could potentially disrupt the magnetosphere, the magnetic field that surrounds Earth and protects us from the solar wind. It could potentially cause a spectacular auroral display, much brighter than normal aurora borealis or aurora australis. The sky would light up with incredible colors from the ionization of atmospheric gases. Depending on the intensity of the radiation, it could potentially cause other effects. It could increase the ionization of the upper atmosphere to levels that disrupt radio communications. It could potentially cause damage to satellites in orbit. It could potentially increase radiation exposure on the ground, though probably not to lethal levels unless the explosion was extraordinarily intense. But here's the key question. Would it be immediately life-threatening? Would the radiation from a tidal disruption event at the center of the Milky Way kill most life on Earth? The answer, surprisingly, is probably not. The distance of 26,000 light-years provides a lot of protection. The radiation would be intense compared to normal space conditions, but not so intense that it would sterilize the planet. The atmosphere would provide shielding. The magnetosphere would deflect charged particles. Life on Earth would feel the effects, but probably wouldn't be immediately catastrophized. However, there are scenarios where things could get worse. If a tidal disruption event happened even closer, or if there was somehow a combination of multiple catastrophic events happening at the same time, then things could become genuinely dangerous. And if there was a black hole closer to us than Sagittarius, a star, if somehow there was a rogue black hole wandering through our neighborhood of the galaxy, then the consequences could be more severe. In fact, astronomers have found evidence that rogue black holes do exist. Black holes can be ejected from binary systems where two black holes are orbiting each other, or from the centers of galaxies through gravitational interactions. So in principle, there could be a black hole out there somewhere closer to us than the center of the galaxy. The odds are low, but they're not zero. If such a black hole was close enough and massive enough, and if a star happened to wander too close to it and got torn apart, the explosion could potentially have more severe consequences for Earth. But based on what we know about the distribution of black holes and the rarity of close encounters, the odds of something like that happening in the near future are extremely low. We're probably safe, at least for now, at least from that particular hazard. There are plenty of other ways the universe can kill you, but a tidal disruption event from a nearby black hole is probably pretty far down the list of existential threats to worry about. That's the thing about studying these extreme cosmic phenomena. It's not just about satisfying curiosity, though, that's important. It's also about understanding the universe well enough to assess genuine risks to our existence. It's about expanding our perspective. It's about realizing how vast and violent the universe is. It's about understanding our place in that vast, violent cosmos. We live on a small planet orbiting an ordinary star in an ordinary galaxy, but we have the capability to observe and study the extraordinary phenomena happening throughout the universe. We can look back in time and witness events that happened billions of years ago. We can detect the most violent explosions in the universe from across unimaginable distances. And when we do detect something like J2245 plus a 3743, when we capture data on a star being torn apart by a black hole, when we measure the brightness and collect the spectra and understand the physics behind it, we're doing something profound. We're expanding human knowledge. We're pushing the boundaries of what we understand about the universe. We're participating in a long tradition of astronomy and observation that goes back thousands of years. The ancient astronomers looked up at the stars and wondered what they were. Modern astronomers look at the same stars and know that we're looking at the past. We're looking at light that took years or decades or millions or billions of years to reach us. We're reading the history of the universe in the light coming from distant sources. And occasionally, if we're lucky, and our instruments are good enough, and our telescopes are pointed in the right direction, we catch something extraordinary. We catch something that reminds us just how powerful and how violent the universe actually is. Now here's something that actually blows my mind when I think about it. We detected this explosion, we measured it, we gathered data on it, we figured out what was happening, and we did all of this using instruments here on Earth. We didn't have a spaceship out there measuring things up close. We didn't have a probe near the black hole sending back telemetry. We had telescopes on the ground and in orbit, and using those telescopes and the data they collected, we managed to piece together an understanding of what was happening billions of light years away. The technology that made this possible is genuinely remarkable. The first detection came from the Zwicky Transient Facility, or ZTF as everyone calls it. This is an instrument located at Palomar Observatory in California. The Zwicky facility is specifically designed to look for things in the sky that change. Its entire purpose is to scan the cosmos looking for transients, objects that appear and disappear and change over time. Supernovas, variable stars, asteroids, gamma-ray bursts, whatever. If something is changing brightness or position, ZTF is designed to catch it. The way ZTF works is it takes images of the sky repeatedly, multiple times per night. It compares the images from night to night. It looks for things that are brighter in one image than they were in a previous image, or dimmer, or that have moved, or that have disappeared entirely. It's essentially a change detection system, and it covers a huge area of the sky, multiple times per night, automatically, without human operators sitting at the telescope manually searching for objects. When J2245 SA3743 first showed up in the ZTF data in 2018, it was flagged as an object of interest. Something was changing in that location, something that hadn't been there before, or that was changing brightness. The ZTF system automatically sent alerts out to the astronomical community. Hey, we've detected something interesting. You might want to take a closer look. And astronomers did take a closer look. They pointed more powerful telescopes at the location. They started gathering more detailed data. They used spectroscopy to analyze the light coming from the object. Spectroscopy is a technique where you break down the light into its component wavelengths, like a prism creates a rainbow. By analyzing the spectrum, you can figure out what elements are present, how hot things are, what the physical conditions are in the source of the light. The spectrum from J22245 plus a 3743 showed signatures of hot material. The peak of the spectrum was in the ultraviolet range, which told astronomers that the source was extremely hot, hotter than any normal star, hotter than the surface of any star in the galaxy. This suggested an accretion process where material is falling into something and being heated to extreme temperatures. But it could have been several different things at that point. It could have been a binary system where one star is pulling material from another star. It could have been an active galactic nucleus, where a black hole at the center of a galaxy is consuming material. It could have been something else entirely. The initial data wasn't definitive. It just showed that something hot and bright had turned on. So the astronomical community continued to observe. They kept monitoring J2245 plus 3743 with multiple telescopes. The Palomar Observatory was gathering data. Other ground-based telescopes were doing follow-up observations. And satellites in orbit, X-ray observatories and ultraviolet observatories and infrared observatories, all of them were being pointed at the location. Everyone wanted to collect as much data as possible on this interesting object. Over the following months, as the brightness increased, and the spectrum continued to show these signs of extremely hot material, the picture became clearer. This wasn't a binary star system. The light curve didn't match anything from a normal stellar process. And by comparing the observations to theoretical models, astronomers started to suspect that what they were seeing might be a tidal disruption event. But even that didn't become fully clear until years later, after collecting years' worth of data. Because the key signature of a tidal disruption event is a specific pattern in how the brightness changes over time. The light curve has a characteristic shape. If you plot brightness versus time, a tidal disruption event produces a specific mathematical relationship. The brightness rises relatively quickly, reaches a peak, and then declines more slowly. The exact shape depends on various parameters, like the mass of the black hole, the mass of the star, the distance from the black hole, and so forth. By 2021-2022, after years of continuous observation, the light curve of J2245 plus 3743 was starting to match the theoretical predictions for a tidal disruption event. It was showing the right pattern. It was following the predicted mathematical relationship. And by November 2025, when the peak brightness was reached, the identification was essentially certain. This was a tidal disruption event. This was a star being torn apart by a black hole. Now, the instruments that were collecting this data, they weren't just simple telescopes. These were sophisticated instruments with sensitive detectors. The Zwicky Transient Facility has a wide-field camera that can cover a large area of the sky. It has a detector that's sensitive to optical light, the visible light that human eyes can see, plus ultraviolet and infrared that we can't see but that telescopes can detect. Then there were specialized X-ray observatories in orbit, satellites like XMM Newton, launched by the European Space Agency, and Chandra, launched by NASA. These satellites have detectors that are sensitive to X-rays. The X-ray observations were crucial because during the peak of the explosion, much of the energy was being released in the X-ray portion of the spectrum. If you only looked at visible light, you'd miss most of what was happening. There were also infrared observatories. Infrared is long-wavelength radiation, heat radiation essentially. By observing in infrared, astronomers could see through dust that might otherwise block the visible light. They could see the details of what was happening without being obscured by intervening material. And then there were radio telescopes. Radio waves are even longer wavelength than infrared. Radio telescopes are good at detecting radiation that's been scattered or that's coming from cooler regions. By observing at radio wavelengths, astronomers could get information about the cooler material surrounding the hot core of the explosion. All of these different observations, taken at different wavelengths, combined together to give a complete picture. It's like having someone describe a scene to you in black and white, and then having someone else describe it in color, and then having a third person describe it from a different angle. Each observation adds a piece to the puzzle. Each telescope provides a different view of what's happening. The light from J2245-3743 was being studied from Earth-based observatories and from space-based observatories, from the ground, in the infrared and visible, from orbit, in the X-ray, ultraviolet, and infrared. The data from all of these different sources was being combined and analyzed, and it all pointed toward the same conclusion. A star had been torn apart by a black hole, and we were witnessing the aftermath of that destruction. One of the most important pieces of information came from detailed X-ray observations. The X-ray spectrum showed specific emission lines, specific wavelengths of X-rays that were brighter than the surrounding spectrum. These emission lines come from specific elements. You get emission lines from iron, from oxygen, from nitrogen, from carbon. All the elements that made up the star, now existing as ionized atoms in the superheated material surrounding the black hole, emitting X-rays. By analyzing these emission lines, astronomers could determine the temperature of the material, the density, the velocity at which it was moving. They could get a sense of what was actually happening physically. They could see that material was indeed falling into the black hole at high speeds. They could see that it was being heated to billions of degrees. They could see that it was producing radiation across the entire electromagnetic spectrum. The data also gave astronomers information about the black hole itself. By analyzing how the radiation changed over time, by fitting the observations to theoretical models of accretion onto black holes, they could estimate the mass of the black hole, and the estimates consistently came out to around 500 million solar masses. This confirmed that they were dealing with an extremely massive black hole, much more massive than most black holes that have been studied before. The redshift of the light also provided information. Redshift is a phenomenon where light from distant objects is shifted toward longer wavelengths because the universe is expanding. By measuring the redshift of J2245-3743, astronomers could determine its distance. The calculation showed that it was about 10 billion light-years away. That number combined with the brightness measurement confirmed that this explosion was extraordinarily energetic. It had to be to appear as bright as it did from such a great distance. All of this analysis required sophisticated data processing and modeling. Astronomers and physicists worked together to fit the observations to theoretical models. They ran simulations on computers to see if the predicted light curves from tidal disruption events matched the observed light curves. They compared different models to see which one best explained the data. They published papers describing their analysis and their conclusions. And importantly, the astronomical community engaged in peer review. Other astronomers and physicists read the papers, checked the math, looked at the data, and evaluated whether the conclusions were justified. In some cases, they found errors or had different interpretations. In other cases, they confirmed the findings and built upon them. This is how science works. Claims are made, they're scrutinized, they're tested against observations and against theory, and only when they survive that scrutiny do they become accepted as true. In this case, the evidence for a tidal disruption event was compelling. The light curve matched the predictions. The spectrum matched the predictions. The behavior over time matched the predictions. Every piece of data that was collected pointed toward the same explanation. So the astronomical community came to accept the conclusion. This was a tidal disruption event. This was a star being destroyed by a black hole. This was the most luminous such event ever recorded. And the technology that made it possible to reach this conclusion represents the pinnacle of modern observational astronomy. We're talking about instruments with sensitivity to detect individual photons. We're talking about detectors that can measure changes in brightness to incredible precision. We're talking about telescopes that can resolve details in distant objects. We're talking about satellites in orbit that can collect data free from the interference of Earth's atmosphere. We're talking about computational resources that can process terabytes of data and run complex simulations. None of this existed 100 years ago. 100 years ago, if you wanted to observe the sky, you pointed a telescope at the stars, and you looked through the eyepiece yourself. You drew pictures of what you saw. You counted objects. You manually searched for anything unusual. The idea that you could scan the entire sky multiple times per night, automatically detect objects that were changing, gather detailed spectroscopic data on millions of objects, and analyze it all with computers, that was science fiction. But now it's reality. We have the capability to observe the universe at scales and sensitivities that would have been unimaginable to past generations of astronomers. We can detect individual photons. We can measure brightness changes of fractions of a percent. We can analyze the light from objects so distant that the light has been traveling for billions of years to reach us. We can use that light to understand the physics of the most extreme environments in the universe. And J2245+3743 is a perfect example of this capability. We detected an explosion that happened 10 billion years ago. We gathered detailed information about it. We figured out what physical process caused it. We understood the extreme physics involved. And we did it all using instruments and techniques that represent the combined effort of thousands of scientists and engineers over many decades of technological development. Looking forward, the capabilities are only going to improve. New telescopes are being built that will be even more sensitive, even more capable of detecting faint objects and analyzing their properties in detail. The James Webb Space Telescope is already revolutionizing astronomy by allowing us to see objects from the early universe with unprecedented detail. Future telescopes like the Vera-Rubin Observatory will scan the sky continuously and will detect transient events with even greater sensitivity than ZTF. In a few years, when the Roman Space Telescope launches, we'll have additional capabilities in infrared and optical astronomy. The combination of all these instruments will give us a comprehensive view of the universe and the ability to detect and study events like tidal disruption events more thoroughly than ever before. We'll be able to characterize the properties of these events. We'll be able to search for tidal disruption events that occurred even earlier in cosmic history. We'll be able to learn more about black hole physics and the processes that destroy stars. And that's the beautiful thing about science. You make an observation, you gather data, you analyze it, you understand something about the universe that you didn't understand before, and then you use that knowledge to improve your instruments and your techniques so that you can make even better observations and understand even more. It's a continuous process of improvement and discovery. J22453743 represents a milestone in that process. It's the brightest tidal disruption event ever recorded. It's taught us about the limits of black hole physics. It's shown us that extreme phenomena in the early universe can still be detected and studied today. It's demonstrated the power of modern observational astronomy. And it's a reminder that the universe has plenty of surprises left to discover. There are mysteries waiting to be solved. There are phenomena waiting to be observed. And we have the technology to do the observing. There's one more crucial thing that makes J2245+3743 so important to astronomers, and it's something that goes right to the heart of one of the biggest mysteries in cosmology. When this explosion was happening, when this star was being torn apart 10 billion years ago, the universe was only 3.8 billion years old. Think about that. The universe today is 13.8 billion years old. When this event occurred, the universe was less than 30% of its current age. It was young. It was still in the process of forming galaxies and structures on the largest scales. And the black hole that did the tearing, the 500 million solar mass monster at the center of that distant galaxy, that black hole shouldn't have existed at that time, or at least that's what theoretical physicists have been struggling with for years. This is one of the biggest unsolved problems in cosmology. We call it the black hole growth problem. Here's the issue. Black holes form when massive stars reach the end of their lives and explode as supernovas. The core of the star collapses and forms a black hole. The smallest black holes we know about have masses of about 5 solar masses. That's about 5 times the mass of our Sun. These stellar mass black holes are relatively common. We've found hundreds of them in our galaxy and in nearby galaxies. But supermassive black holes are different. These are black holes with masses millions or billions of times the mass of the Sun. Most large galaxies have a supermassive black hole at their center. Our own galaxy has Sagittarius A star, which is 4 million solar masses. The black hole in the galaxy M87 is 6.5 billion solar masses. These things are enormous, and they seem to be closely related to the properties of the galaxies they inhabit. The bigger the galaxy, the bigger the black hole at its center tends to be. But here's the problem. If you do the math, if you start with stellar mass black holes, and you calculate how fast they can grow by accreting material and merging with other black holes, you can't grow a billion solar mass black hole in the time available if the universe is only 13.8 billion years old. There just isn't enough time. The growth is too slow. And yet observations show that supermassive black holes were already present in the early universe. Billions of years ago, we see galaxies that have supermassive black holes. And some of those black holes are absolutely enormous, hundreds of millions or billions of solar masses. How did they get that big so fast? That's the black hole growth problem. And it's been bothering cosmologists for decades. One way that black holes can grow quickly is through accretion, where they consume material around them. If a black hole is actively eating material, if it's surrounded by an accretion disk of material falling in, then the black hole can grow relatively quickly. But accretion can only go so fast. There's a limit to how much material can fall into a black hole per unit time, determined by something called the Eddington limit. Beyond that limit, the radiation pressure from all the energy being released blows away the material that would otherwise fall in. Another way that black holes can grow is through mergers. Two black holes can orbit each other and gradually spiral inward due to gravitational waves. Eventually they collide and merge, forming a larger black hole. But mergers are relatively rare events. They don't happen constantly, and for them to accumulate enough mergers to create billion solar mass black holes in the early universe, you'd need the right conditions. You'd need a high density of black holes. You'd need a lot of dynamical interactions in dense stellar environments. So the question is, how did the supermassive black holes in the early universe grow so quickly? How did they reach such enormous masses in such a short time? This is still an open question. There are several theories. Some astronomers think that the seed black holes that start the growth process might be larger than we thought, maybe formed through different mechanisms than normal stellar collapse. Some think that accretion rates might be higher in the early universe than we currently assume. Some think there might be more mergers happening. The truth is probably a combination of several factors. But here's where J2245 plus 3743 comes in. By studying tidal disruption events, by seeing how stars interact with black holes, by measuring the properties of black holes through these violent interactions, we get information that helps us constrain the black hole growth problem. We learn more about how black holes actually work. We learn about the processes by which they consume material. We learn about the efficiency with which mass is converted to energy during accretion. Every tidal disruption event is like a natural experiment, where a star provides a large package of material to the black hole all at once. The black hole consumes this material rapidly. We can observe the process and study it. We can see how efficiently the energy is released. We can measure the timescales over which accretion happens. All of this information helps constrain our models of black hole physics. And the fact that we found this event, that we detected it and studied it, means we can search for more such events. If tidal disruption events are happening in galaxies throughout the universe, and if some of those events are happening in the early universe, then by studying those events, we can learn about the black holes in the early universe. We can learn about the properties of galaxies in the early universe. We can learn about how galaxies and black holes co-evolve. The connection between black holes and galaxies is profound. The mass of the central black hole is related to the mass of the galaxy. The properties of the black hole seem to influence how the galaxy evolves. In some cases, the energy from accretion onto the black hole can heat up the gas in the galaxy and prevent it from forming too many stars. This is called feedback, and it's thought to be crucial in regulating how big galaxies can grow. So when we study a tidal disruption event in a galaxy far away, we're not just studying the physics of star destruction, we're studying galaxy evolution, we're studying the relationship between black holes and galaxies, we're studying the history of the universe itself, and looking at J2245 plus 3743 specifically, the black hole there is part of a galaxy. That galaxy formed sometime in the past, and it evolved to its current state. The black hole at its center grew to 500 million solar masses. Stars formed in the galaxy. The galaxy interacted with other galaxies, and at some point, by chance, a star wandered too close to the central black hole and got torn apart. When we observe this event, we're observing a snapshot of what that galaxy looks like, frozen in time 10 billion years ago. We can see what kind of galaxy it is. We can measure its properties. We can understand how it compares to galaxies in the local universe, galaxies around us today. And through such comparisons, we can understand how galaxies have evolved over cosmic time. The light from this galaxy also tells us about the composition of the star that was torn apart, the elements in the star's atmosphere, the chemical abundances. This tells us something about how the star formed and what materials were available in that galaxy at that time. It tells us about the chemical evolution of the universe. Early in cosmic history, when the first stars formed, there were very few heavy elements because they hadn't been created yet. The early stars were made mostly of hydrogen and helium, but later, as stars lived and died and created heavy elements through nuclear fusion, those elements were spread into the galaxy. Later stars incorporated those elements. Galaxies became more enriched with heavy elements over time. By studying the spectrum of the destroyed star in J22245 plus 3743, astronomers can measure the abundances of various elements. And that tells them something about what the galaxy was like at that time, how much chemical evolution had already happened, how many generations of stars had lived and died, and enriched the galaxy with heavy elements. This kind of information is valuable for understanding galaxy evolution. Combined with observations of other galaxies at various distances and epochs, astronomers can piece together a picture of how galaxies have changed over time. They can understand the history of star formation in galaxies. They can understand how galaxies have grown from small beginnings to large structures like the Milky Way. And then there's the question of how common tidal disruption events actually are. We've now detected one that's extraordinarily bright, but how often do these events happen? In a typical galaxy, maybe once every 100,000 years or so, but with billions of galaxies in the observable universe, that means tidal disruption events are happening somewhere on average all the time. In fact, they're probably happening multiple times per day somewhere in the observable universe. Most of them we never see. They happen too far away, or they happen in directions we're not looking, or they're not quite bright enough to detect with our current instruments. But some of them, if they're bright enough, if they're close enough, if we have our instruments pointed in the right direction, we can detect them, and we do. Astronomers have found several dozen tidal disruption events over the past couple decades as observation techniques have improved. But J2245+3743 is special because it's so bright. It's the brightest one. And that brightness gives us an opportunity, because the brighter the explosion, the farther away we can detect it. A tidal disruption event like J2245+3743, even from 10 billion light-years away, is still detectable. That means we could potentially detect even older tidal disruption events from even earlier in cosmic history, events from when the universe was younger still. Imagine detecting a tidal disruption event from when the universe was only a couple billion years old. That would give us information about galaxies and black holes from an even earlier epoch. It would help us understand how the earliest galaxies formed and evolved. It would help us understand how the first supermassive black holes formed and grew. It would shed light on some of the deepest questions in cosmology. This is why astronomers are so excited about J2245+3743. It's not just that it's the brightest explosion ever detected, it's that it opens up new possibilities for what we can study. It shows us that even extremely distant and ancient events can leave traces that we can detect today. It expands our cosmic horizon. It gives us access to the early universe in ways we didn't have before. And as new telescopes come online, as we improve our detection capabilities, we'll be able to find more such events. We'll be able to detect more tidal disruption events. We'll be able to characterize their properties. We'll be able to study the black holes and galaxies involved. We'll be able to use them as probes of the universe's history. Some astronomers have started talking about using tidal disruption events as cosmic laboratories. They're like nature's way of giving us information about extreme physics. They're like experiments that the universe is running for us. We just have to be smart enough to observe them and interpret the results. And that's the deeper significance of J2245+3743. It's not just one bright explosion. It's a key that unlocks new ways of studying the universe. It's a reminder that the cosmos is full of surprises. It's a demonstration of how much we can learn by careful observation and analysis. It's an invitation to look deeper, to search harder, to find more such events, to understand the universe at deeper and deeper levels. The story of J2245+3743 is the story of human curiosity. It's the story of how we use technology to overcome the vast distances of space and time. It's the story of how we've learned to read the universe's history written in light. And it's a story that's far from over. There are more discoveries waiting to be made, more mysteries waiting to be solved, more explosions waiting to be observed. The universe has plenty of secrets left, and we're only just beginning to uncover them. So we've got this incredible discovery. We've got an explosion that happened 10 billion years ago. We've measured its brightness. We've understood the physics behind it. We've recognized its significance for understanding black holes and galaxies. But the question that moves beyond just this one event is this: what comes next? What's the future of studying phenomena like this? How does this discovery change astronomy going forward? The answer is that J2245+3743 represents a threshold. It's a demonstration of what's possible with current technology. But it's also a challenge and an inspiration for what we can do in the future. Because now that we know such bright tidal disruption events can be detected from such vast distances, we can start to ask more sophisticated questions. We can design observations specifically to catch these events. We can look for them systematically. We can build up a census of how common they are, how bright they can get, what the range of their properties is. Right now, the tidal disruption events we've found have been somewhat accidental. We weren't specifically looking for them. ZTF was designed to catch transient events in general. It caught supernovas, gamma-ray bursts, variable stars, and among those, some tidal disruption events. But now that we understand what to look for, now that we know what the signatures of a tidal disruption event look like, we can be more systematic. We can tune our instruments and our search algorithms to preferentially find them. The next generation of sky surveys are going to be incredibly powerful. The Vera-Rubin Observatory, scheduled to start operations soon, will scan the entire sky multiple times per night using what's called the Legacy Survey of Space and Time. Multiple times per night. That's 3 times more frequently than ZTF. The Vera-Rubin Observatory will be looking for transient events continuously. It's going to find a lot more tidal disruption events than we've found so far. We're also going to get help from space-based observatories. The James Webb Space Telescope has already started revolutionizing infrared astronomy. It's capable of seeing objects from the early universe with unprecedented detail. While JWST isn't specifically designed as a transient survey instrument, it can certainly be pointed at interesting objects for follow-up observations. And there are proposals for future space telescopes that would be specifically designed to search for transient events in the infrared and ultraviolet. The Roman Space Telescope, which NASA is planning to launch in the next few years, will have infrared capabilities superior to JWST in some ways, and it will have a wide field of view suitable for surveying the cosmos. Roman could potentially discover many more tidal disruption events, including some from even earlier in cosmic history than J2245 plus 3743. And then there are the radio telescopes. Radio astronomy has been advancing rapidly. The Very Large Array has been upgraded. The Atacama Large Millimeter Array in Chile is producing incredible data. Radio observations can penetrate dust that obscures visible light. Radio observations can detect the jets and outflows that sometimes accompany tidal disruption events. The Square Kilometer Array, currently under construction, will be the most sensitive radio telescope ever built. When it comes online, it will open up entirely new discovery space for transient phenomena. So the infrastructure is being built, the technology is advancing, we're going to find more tidal disruption events. Some of them will be bright and nearby, relatively speaking. Some of them will be fainter and more distant. Some of them might have unusual properties that challenge our current understanding. And each one will teach us something new. But beyond just finding more events, there's the question of what we do with them. How do we leverage these discoveries to advance our understanding of fundamental physics? One approach is to use tidal disruption events to constrain black hole properties. Each event depends on the mass of the black hole, the mass of the star, the initial orbit of the star, various other factors. By observing many events and fitting them to theoretical models, we can learn the distribution of black hole masses in the universe. We can learn how common different kinds of black holes are. We can understand the relationship between black holes and their host galaxies. Another approach is to use tidal disruption events to study accretion physics. When material falls onto a black hole and releases energy, the details of how that energy is released depend on the physics of accretion, the magnetic fields involved, the gas dynamics, the radiative processes. By observing tidal disruption events in detail, we can test our models of accretion. We can refine our understanding of how black holes consume material. There's also the possibility of using tidal disruption events to test general relativity in extreme conditions. General relativity has been tested in many ways, but mostly in relatively weak gravitational fields or in systems where the effects are small. Near a black hole, the effects of general relativity are extreme. The curvature of space-time is severe. If there are any deviations from Einstein's predictions, they might show up in the behavior of tidal disruption events. By comparing observations to predictions from general relativity, we can test whether Einstein's theory continues to hold in these extreme environments. And there's the possibility of discovering new physics entirely. Maybe there are processes happening near black holes that we haven't anticipated. Maybe there are phenomena that emerge from the interaction of matter and extreme gravity that surprise us. History shows that whenever we build better instruments and observe the universe in more detail, we find unexpected things. We find phenomena that don't fit neatly into our current theories. Those surprises are how science advances. For example, when gamma-ray bursts were first discovered, nobody expected them. They were a complete surprise. And the effort to understand gamma-ray bursts led to insights into stellar evolution, neutron stars, black holes, and relativistic jets. The universe produced these phenomena, and we had to figure out what was going on. Tidal disruption events could be similar. They might be the key to unlocking new understanding about extreme physics. There's also the possibility of using tidal disruption events in conjunction with gravitational wave detectors. When two black holes merge, they produce gravitational waves that we can detect with instruments like LIGO and Virgo. If a tidal disruption event happened to involve a black hole merger, or if it affected the dynamics of a black hole binary system in some way, we might be able to detect the gravitational waves from the merger, while also observing the electromagnetic radiation from the tidal disruption event. This multi-messenger astronomy, combining observations from different wavelengths and different types of radiation, is becoming an increasingly important tool for understanding extreme cosmic phenomena. The detection of gravitational waves from black hole mergers and neutron star mergers over the past decade has shown the power of multi-messenger astronomy. When LIGO detected the merger of two neutron stars in August 2017, telescopes all over the world rushed to observe the location. They captured X-rays, gamma rays, infrared radiation, radio waves. Combined, all these observations told a detailed story of what happened. The story wouldn't have been nearly as complete if we only had gravitational wave data or only had electromagnetic data. By combining them, we got a much richer understanding. Similarly, if we could detect gravitational waves from a black hole system while simultaneously observing a tidal disruption event, we'd learn far more than we could from either observation alone. This might seem like a long shot, but these are the kinds of opportunities that keep astronomers excited about the future. There's also the possibility of learning about stellar populations in distant galaxies through tidal disruption events. When a star gets torn apart, we can measure its properties through its spectrum. We can learn about its mass, its composition, its age. By observing many tidal disruption events in a particular galaxy, we could start to understand the stellar population in that galaxy. What kinds of stars are there? How are they distributed in mass? What's their chemical composition? This information is normally hard to get for distant galaxies, but tidal disruption events could provide a novel way to study it. And then there's the question of using tidal disruption events to search for exotic objects. Most of the time, when a tidal disruption event occurs, it's a normal star getting torn apart. But what if something unusual happened? What if a neutron star got too close to a black hole? What if a stellar mass black hole wandered too close to a supermassive black hole and got disrupted? These would produce unusual signatures in the data. They might be rare, but they might exist. Finding them would tell us about the dynamics and populations of different kinds of objects in the centers of galaxies. In fact, there have been suggestions that some tidal disruption events might involve the disruption of asteroids or comets rather than stars. A small body wandering too close to a black hole would produce a different signature than a star being torn apart. The radiation would be different. The timescales would be different. By finding such events, we could learn about the populations of small bodies in galactic nuclei. We could understand how asteroids and comets get injected into the dangerous regions near black holes. Looking even further ahead, there's the possibility that in the distant future, when humanity has advanced far beyond where we are now, we might use observations of tidal disruption events for other purposes entirely. Maybe we'd use them to study the evolution of black holes over cosmic time. Maybe we'd use them to map the distribution of black holes throughout the observable universe. Maybe we'd use them as signposts, as beacons that mark interesting regions of space worth studying in more detail. But that's speculation about the distant future. In the nearer term, the challenge is clear. We need to find more tidal disruption events. We need to characterize their properties. We need to use the data to answer fundamental questions about black holes, galaxies, accretion physics, and fundamental gravity. We need to build theoretical models that can explain the observations. We need to make predictions that can be tested with new observations. We need to push the boundaries of what's possible in observational astronomy. And J2245 3743 is just the beginning. It's a proof of concept. It shows that we can detect these events. It shows that we can study them in detail. It shows that they provide insights into extreme physics and cosmic history. Now it's time to systematically search for more. Now it's time to build up statistics. Now it's time to really understand these phenomena. The exciting part is that we're living in the era where this is possible. The technology has advanced to the point where we can detect transient events across the entire observable universe. We have instruments sensitive enough to capture photons from objects 10 billion light-years away. We have computers powerful enough to analyze the data. We have theoretical models sophisticated enough to interpret the observations. All the pieces are in place. All we have to do is use them. And as we do, as we find more tidal disruption events, and study them in detail, we'll be learning the story of the universe. We'll be understanding how galaxies formed and evolved. We'll be understanding how black holes grew to their enormous masses. We'll be probing physics in extreme conditions that we can't reproduce in laboratories. We'll be answering questions that humans have wondered about for millennia. How did the universe form? How did it evolve? What are the fundamental laws of physics? Tidal disruption events are just one tool in our arsenal for answering these questions, but they're a powerful tool. They're a window into a universe that's far more violent, far more energetic, far more interesting than our everyday experience might lead us to believe. And that's the beauty of astronomy. It reveals the cosmos in all its complexity and grandeur. It shows us that reality is far stranger and more wonderful than fiction. It inspires us to keep looking, keep questioning, keep searching for understanding. When you really sit with what J2245 plus 3743 means, when you take the time to let it sink in, something shifts in how you see the universe. It's not just an interesting scientific discovery. It's not just a data point in a catalogue of cosmic phenomena. It's something that changes your perspective on existence itself. It reminds you that the universe is far vaster and far more violent than your everyday experience might suggest. Think about what you just learned. Somewhere out there's a galaxy. In that galaxy, a black hole sits at the center. A hole in space-time so dense, so powerful, that nothing can escape once it crosses a certain boundary. And wandering too close to this hole was a star, a massive star, 30 times the mass of our sun, something that should have been stable and powerful and eternal in human timescales. And gravity reached out and grabbed it, stretched it, tore it to pieces, converted it to radiation, erased it from existence. All of that happened. And we know about it. We know about it not because we sent a probe out there, not because we have any way to directly observe it in real time. We know about it because light, the most fundamental carrier of information in the universe, traveled across 10 billion light years to reach us. Light that began its journey when the universe was young. Light that was already halfway to Earth when humans first learned to make tools. Light that kept traveling through billions of years of cosmic history, through the expansion of space itself until it finally arrived at our doorstep. And we had the foresight and the capability to build instruments sensitive enough to detect that light. We had the intelligence and the dedication to analyze it and understand what it meant. We have the mathematical tools and the physical knowledge to interpret what we saw. We can look at light that traveled across the universe and understand a story of cosmic destruction that happened before Earth existed. That's not trivial. That's not just business as usual for human civilization. That's humanity doing something extraordinary. That's us reaching out mentally across incomprehensible distances and timescales and touching something real. That's us participating in the grand human tradition of seeking understanding. From the first humans who looked up at the stars and wondered what they were, to the ancient astronomers who charted the night sky, to the modern scientists who build instruments and analyze data, all the way back to curiosity and the drive to understand. And what does it all mean? What's the significance of understanding J2245 plus 3743? At the most basic level, it means we understand something about the universe that we didn't understand before. We understand black holes better. We understand gravity better. We understand the processes that destroy stars and release enormous amounts of energy. That knowledge is valuable in itself. It's part of humanity's accumulated understanding of reality. But it goes deeper than that. Every time we understand something about the physical universe, we're answering a question that humans have wondered about for thousands of years. Where do we come from? What is the nature of reality? What are the fundamental laws that govern everything? These aren't just academic questions. These are the questions that define human existence. They're the questions that philosophers and theologians and scientists have struggled with throughout history. And astronomy has a unique role in answering these questions because it gives us access to the past. When you look at a distant star, you're looking at the past. When you look at a distant galaxy, you're looking even further into the past. The universe is essentially a time machine. Light years are literally measuring distance in space, but they're also measuring time. A million light years away means you're looking at light that took a million years to reach you. So you're seeing how things looked a million years ago. And if you look far enough, if you look to the edges of the observable universe, you're looking back to a time when the universe was very young. You're seeing how things looked in the early universe. And that gives you information about how the universe formed and evolved. That gives you information that no other source can provide. You can't recreate the conditions of the early universe in a laboratory. You can't build an experiment that shows you how the first galaxies formed. But you can observe the early universe. You can study light that's been traveling since those ancient times. You can read the history of the universe in the light we receive. J22245 Plo 3743 is just one piece of that history, one chapter in a vast book, but it's an important chapter. It's a chapter that tells us about black holes and galaxies in the early universe. It's a chapter that reminds us how much we still don't understand. Every time we make a discovery like this, we solve some puzzles, but we also uncover new mysteries. We learn more about how things work, but that learning reveals how much we still have to learn. There's also something spiritually significant about all of this. I know that might sound odd coming from a science perspective, but it's worth thinking about. When you really consider what it means to observe something that happened billions of years ago, when you really grasp the scale and the distances involved, when you really understand that you're part of a universe that's so vast and so old and so complex that it exceeds human intuition, it changes something in you. It creates a sense of awe, a genuine sense of wonder. This is the feeling that the universe is profound and beautiful and mysterious. This is the feeling that inspired humans to become scientists in the first place. This is what drives curiosity. This is what makes people want to learn more and understand more and explore further. And that awe is important. It's important for motivating scientific research. It's important for inspiring the next generation of scientists and engineers and explorers. But it's also important for something deeper. It's important for how we see ourselves in the cosmos. Because when you truly grasp the scale of the universe, when you understand that we live on a small planet orbiting an ordinary star in an ordinary galaxy, when you realize that events of unimaginable scale and violence are happening throughout the cosmos constantly, it changes your perspective on human concerns. Many of the things that we worry about, that we stress about, that we think are so important, they seem to fade in significance when you consider the vastness of the cosmos. The universe has been around for 13.8 billion years. Human civilization has existed for maybe 10,000 years. Modern science for maybe 400 years. And in that short span of time, despite being infinitesimally small and infinitesimally brief in cosmic terms, we've managed to figure out an enormous amount about how the universe works. And not only have we figured things out, but we've done it with wonder and curiosity and collaboration. Scientists from around the world, speaking different languages from different cultures, all working together to understand the universe. People with different beliefs and worldviews united by a common drive to understand. That's something beautiful. That's something worth celebrating. Because science, at its heart, is a human endeavor. It's not cold and sterile and without passion, as some people imagine. It's driven by curiosity and wonder and the desire to understand. It's about asking questions and seeking answers. It's about looking at the universe and asking why, how, what's really going on, and then doing the hard work to find those answers. When an astronomer stays up all night analyzing data, when they run simulations on computers to test their theories, when they collaborate with colleagues to interpret observations, they're not just doing technical work. They're participating in something profound. They're seeking to understand reality. They're trying to answer the deepest questions about existence. And discoveries like J2245 plus 3743, they validate that effort. They show that the hard work pays off. They show that we can indeed understand the universe. We can reach across billions of light years. We can detect ancient light. We can interpret what that light means. We can understand processes and phenomena that are incomprehensibly distant and ancient. There's also something empowering about it for individuals who might feel small or insignificant, understanding that we've managed to figure out these profound truths about the universe, that we're capable of reaching so far and understanding so much, that can be uplifting. It shows the potential of human intelligence and human curiosity. It shows what we're capable of when we direct our attention and resources toward understanding. And practically speaking, the spin-offs from this kind of research are enormous. The technology developed to detect J2245 plus 3743, the instruments used, the computational methods employed, all of these have applications beyond astronomy. Sensitive detectors end up in medical imaging devices. Computational methods developed for analyzing astronomical data end up being used in other fields. The knowledge about physics that comes from studying extreme phenomena ends up being useful for developing new technologies. But even setting aside practical applications, there's value in pure understanding. There's value in knowing how the universe works just for the sake of knowing. There's value in satisfying human curiosity. There's value in expanding the boundaries of human knowledge. These are things that make us distinctly human. The drive to understand, to explore, to push boundaries, to seek knowledge for its own sake. These are fundamental aspects of what makes us who we are. When you look at the history of humanity, the greatest achievements have often come from this drive to understand and explore. The great works of science and philosophy and art have all come from people who wondered about the world and sought to understand it. And in our time, in the 21st century, one of the great frontiers of understanding is astronomy. It's the study of the cosmos. It's the attempt to understand the universe at the deepest levels. And we're living in an era where this is possible. We have the technology, we have the knowledge, we have the resources. We can do science at a level that would have seemed like magic to people just a century ago. We can detect individual photons from objects billions of light years away. We can measure the composition of distant stars. We can understand the physics of extreme phenomena. We can map the universe and understand its history. This is an incredible time to be alive, an incredible time to be curious about the cosmos, an incredible time to participate in the grand human quest for understanding. Whether you're a professional astronomer or just someone who likes to look up at the stars and wonder about them, you're part of that quest. You're part of the human tradition of seeking knowledge about the universe. And J2245 plus 3743 is a reminder of why that quest is worthwhile. It's a reminder that the universe is stranger and more wonderful than we often imagine. It's a reminder that there are profound truths waiting to be discovered. It's a reminder that human beings, despite being infinitesimally small in cosmic terms, are capable of extraordinary achievements in understanding. It's a reminder that curiosity is a force for good, that seeking knowledge and understanding is something valuable and important. So the next time you look up at the stars, remember that. Remember that those little points of light are actually distant suns, some of them with their own planets, their own worlds. Remember that the light you're seeing has traveled for years or decades or billions of years to reach you. Remember that every photon carrying that light is a messenger from the cosmos, bringing information from across vast distances and timescales. Remember that humans have built instruments and developed knowledge to detect and interpret those messages. Remember that we've figured out astounding things about how the universe works. And remember that this is just the beginning. There are more discoveries waiting to be made. There are more mysteries waiting to be solved. There are more wonders waiting to be revealed. The universe has plenty of secrets left, and we're only just beginning to uncover them. Every discovery like J2245 plus 3743 is a stepping stone toward greater understanding. Every question answered leads to new questions. Every mystery solved reveals deeper mysteries. That's what makes this an exciting time. That's what makes astronomy and science in general so compelling. We're on a journey toward understanding. We're exploring the cosmos. We're seeking knowledge about reality. And along the way, we're being reminded of how profound and beautiful the universe actually is. Let me bring this back to something fundamental that I think gets lost sometimes when we're discussing all these massive numbers and cosmic distances and ancient explosions. Let me bring this back to you, right now, in this moment. What does any of this actually mean for you as a human being living in 2025? Here's the thing that really hit me when I was learning about J2245 plus 3743. Everything you see around you, everything you experience every day, the people you love, the places you go, the things you worry about, all of that exists on a planet, a physical object in space. And that planet is orbiting a star, a nuclear fusion reactor that's been burning hydrogen into helium for the last 4.6 billion years. And that star is part of a galaxy, a collection of hundreds of billions of stars spiraling around each other in a gravitational dance. And that galaxy, our galaxy, the Milky Way, it's part of a local group, which is part of a larger cosmic structure, which is part of the observable universe that extends for 46 billion light-years in every direction. And within that universe, right now, at this very moment, there are processes happening that are so violent and so energetic that they make nuclear weapons look like fireworks. Stars are being torn apart. Black holes are consuming material. Galaxies are colliding. Supernovas are detonating. The universe is in a constant state of dramatic transformation. And most of the time, we don't think about any of that. We go about our daily lives. We worry about work and relationships and bills. We scroll through our phones. We watch television, we eat dinner, we sleep, and we don't think about the fact that we're living on a planet in a cosmos that's absolutely teeming with incredible phenomena happening at scales we can barely imagine. But then something like J2245 plus 3743 happens, or you take the time to really think about it, or you read something that explains it clearly, and suddenly it hits you. The universe is huge. The universe is old. The universe is violent and beautiful and mysterious. And you're a tiny part of it. You're a collection of atoms that has somehow become conscious. You're a pattern of matter and energy that has developed the ability to think about the universe and try to understand it. That realization, that shift in perspective, it changes something. It's humbling. It's awe-inspiring. It makes your everyday problems seem smaller and larger at the same time. Smaller because they're happening on an infinitesimally small scale in an incomprehensibly large cosmos, but larger because they're happening to a conscious being who's capable of understanding the universe. And that consciousness, that ability to understand, that's genuinely remarkable. Think about it from a cosmic perspective. The universe has been around for 13.8 billion years. In all that time, with all the galaxies and stars and planets that have existed, how many of them have developed intelligent life? How many have developed consciousness? How many can look up at the stars and ask questions about what they see? We don't know, but we do know that at least one has, our planet, our species. And not only have we developed consciousness and the ability to ask questions, but we've also developed the capability to answer some of those questions. We've figured out the laws of physics. We've built instruments to observe the universe. We've developed mathematics to describe what we observe. We've created a systematic process for testing theories against evidence. We've built a body of knowledge about how the universe works that's genuinely impressive. And that knowledge is still growing. Every year we know more. Every new discovery reveals new mysteries, but also provides answers to old questions. The trajectory of human understanding has been generally upward. We know more than we did a century ago. We'll know more a century from now than we do today. And part of that future knowledge will come from studying events like J22245 plus 3743. But here's what's really important to understand. The knowledge we're gaining, the understanding we're developing, it's not just for the sake of accumulating information. It's not just so we can publish papers and get citations and build careers in academia, though those things matter too. But the deeper significance is that we're expanding the boundaries of human understanding. We're pushing back the darkness of ignorance. We're illuminating the universe through the light of reason and observation and logic. And that matters. That's not nothing. That's actually profoundly important for the future of humanity, because the more we understand about the universe, the better equipped we are to make decisions about our future. The more we understand about physics and chemistry and biology, the better we can solve problems. Climate change, disease, resource depletion, all of these challenges that humanity faces, they require scientific understanding to solve. We need to understand how the planet works. We need to understand how systems interact. We need to understand the consequences of our actions. And the habit of mind that we develop through science, through careful observation and logical reasoning, that habit carries over into other areas. It teaches us to question assumptions. It teaches us to look for evidence. It teaches us to test theories before accepting them as true. These are valuable habits of mind. These are ways of thinking that can help us solve all kinds of problems, not just scientific ones. So when we study J22245 plus 3743, when we investigate how stars get torn apart by black holes, when we push the boundaries of observational astronomy, we're not just satisfying curiosity, we're building capacity, we're developing understanding, we're preparing humanity for the future, we're learning to think in ways that will help us face challenges ahead. And there are challenges ahead, serious challenges. Climate change is real and it's accelerating. Resource depletion is a genuine concern. Geopolitical tensions are rising. There are plenty of reasons to worry about the future, but there are also reasons to be hopeful, because humanity has shown an incredible ability to adapt and innovate. We have the intelligence to solve these problems. We have the technology. What we need is the will to apply that intelligence and technology to address the challenges. And I think studying the cosmos, understanding how vast and beautiful it is, understanding how small and brief our existence is in cosmic terms, I think that can help with that. It can give us perspective. It can remind us that we're all on the same small planet together. It can help us see past our differences and recognize our common humanity. It can inspire us to work together toward a better future, because ultimately that's what science is about. It's about curiosity, yes. It's about seeking understanding, absolutely. But it's also about recognizing our shared condition as inhabitants of this universe. It's about the human drive to understand and improve our situation. It's about cooperation and collaboration toward common goals. It's about using our intelligence to make the world better. And every time we make a discovery like J2245 plus 3743, every time we push our understanding further, every time we answer a question that's been open for years, we're participating in something that goes back thousands of years. We're part of a human tradition of inquiry and discovery. We're standing on the shoulders of giants. We're using the accumulated knowledge of previous generations to reach further than they could. And we're creating the foundation for future generations to reach even further. That's the real significance of this discovery. It's not just that we found the brightest explosion in the universe. It's that we found it, we understood it, we integrated it into our body of knowledge, and we did it collectively as a species working together toward common understanding. That's genuinely remarkable. That's something to be proud of. So when you look up at the night sky, remember that. Remember that those little dots of light are actually distant suns. Remember that the light you're seeing has traveled for years or centuries or billions of years to reach you. Remember that humans have figured out how to detect that light and interpret it. Remember that we've discovered explosions so bright that they can be seen from across the entire observable universe. Remember that you're part of a species that's trying to understand reality at the deepest levels. And remember that you don't have to be a professional astronomer to participate in that understanding. You can read about discoveries. You can learn about the universe. You can think about what it all means. You can feel the sense of wonder and awe that comes from contemplating the cosmos. You can share that wonder with others. You can inspire the next generation of scientists and explorers by showing them how remarkable the universe is. Because that's how science advances. It's not just through individual geniuses making brilliant discoveries. It's through a broad community of people who are curious and engaged. It's through teachers inspiring students. It's through scientists communicating their discoveries to the public. It's through people from diverse backgrounds bringing different perspectives and ideas. It's through global collaboration and the free exchange of information. And we live in an era where that global collaboration is easier than ever before. Scientists can collaborate across continents in real time. Data can be shared instantly. Papers can be published and peer-reviewed rapidly. Someone in Canada can build on research done by someone in Chile who used data from an observatory in California that was discovered by a team in Germany. The boundaries are dissolving. Science is becoming truly global. And that's beautiful. That's how humanity moves forward. That's how we collectively understand the universe and solve the problems we face. Through cooperation, through shared purpose, through the recognition that we're all in this together. So as you finish watching this, as you take in everything we've discussed about J2245 plus 3743 and black holes and tidal disruption events and the early universe, I want you to feel something. I want you to feel the wonder. I want you to feel the awe. I want you to feel the sense that the universe is vast and complex and mysterious and beautiful. I want you to feel inspired to learn more. I want you to feel connected to the human tradition of seeking knowledge and understanding. And I want you to remember that you're part of something larger than yourself. You're part of humanity. You're part of a species that has the capability to understand the universe. You're part of a civilization that's been developed through thousands of years of accumulated knowledge and innovation. You're part of a global community of curious minds working together toward common understanding. That's powerful. That's important. That matters. And that's what J2245+3743 ultimately teaches us. Not just about black holes and stars and cosmic physics, though those things are genuinely interesting and important, but about what we're capable of as a species, about the power of curiosity and inquiry, about the value of understanding, about our place in the cosmos, and what that means for how we live our lives. The universe is waiting to be understood. There are mysteries waiting to be solved. There are phenomena waiting to be observed. There are questions waiting to be answered. And we have the capability to do the understanding, the solving, the observing, and the answering. We have the intelligence. We have the technology. We have the will. All we have to do is keep looking, keep asking, keep seeking, because that's what drives human civilization forward. That's what makes us who we are. That's what connects us to the cosmos and gives our existence meaning. The drive to understand, the curiosity about how things work, the desire to push boundaries and explore new frontiers, the willingness to work together toward common goals. J2245+3743 is just the beginning. There are more discoveries waiting to be made. There are more explosions waiting to be observed. There are more black holes waiting to be studied. There are more mysteries waiting to be solved. The universe is full of them, and we're only just beginning to understand them. The best discoveries are still ahead of us. The greatest insights are still to come, and you're living in the era where that's happening. That's your time. That's your opportunity to participate in the grandest quest of all, the quest to understand the universe and our place in it. We've journeyed together through an incredible discovery. We've traveled 10 billion years back in time. We've witnessed the destruction of a star. We've explored the physics of black holes and gravity and time itself. We've contemplated what it means for humanity to observe and understand such profound phenomena. And now we arrive at the moment where everything comes full circle. This is where we return to what was promised at the very beginning. This is where we confront the ultimate question that started this whole investigation. Remember the opening moment? Remember when I told you about November 3rd, 2025, that date when astronomers looked at their telescopes and saw something so bright, so unprecedented, that it changed everything they thought they knew. That explosion reaching 10 trillion suns. That's not just a number. That's not just a statistic to file away and forget. That's a reminder that the universe is fundamentally different from how we usually imagine it. For most of human history, people looked up at the stars and saw stability. They saw eternal, unchanging lights in the sky. The ancients believed the stars were perfect and immutable, fixed to a crystal sphere that rotated around the Earth. They couldn't have been more wrong, but their error is understandable. The changes in the stars happen on timescales so long that they're invisible to individual human lifetimes. A star might change brightness over millennia. A supernova might appear where nothing was visible before, but that's rare. For most of the night sky, most of the time, nothing seems to change. But the universe operates on many timescales simultaneously. Some changes happen in microseconds. Some happen over billions of years. J2245+3743 shows us that even across the immense distance of 10 billion light-years, even looking back to the ancient past, change is happening. Violent change. Catastrophic change. The universe is dynamic. The universe is alive in a sense. Not alive like a biological organism, but alive in the sense that it's constantly transforming, constantly evolving, constantly doing things that are dramatic and consequential. And we can observe that. We can detect it. We can understand it. That's the miracle of modern science. That's what makes this moment in history so extraordinary. For the first time in human existence, we have the tools to observe the early universe in detail. For the first time, we can see back almost to the beginning. We can watch how galaxies formed. We can study how stars were created. We can observe how black holes consume material. We can understand the processes that shaped the cosmos. Think about what that means. Thousands of years ago, humans were philosophers and theologians trying to understand the universe through logic and faith. A few hundred years ago, we invented telescopes and started making empirical observations. We discovered that there were things in the universe we couldn't see with our naked eyes: moons orbiting Jupiter, nebulae, distant galaxies. We realized the universe was far larger than we'd previously imagined. But even with that expanded view, even knowing that the universe was vast, we couldn't see very far back in time. We could observe the current state of the universe, but we couldn't directly observe how it came to be that way. We had to infer things. We had to reason from observations to conclusions. We had to build models and test test them against the limited data we had. And then, in the latter half of the 20th century, something changed. We developed technology sensitive enough to detect faint sources. We launched telescopes into orbit above Earth's atmosphere. We built instruments that could measure the spectrum of distant objects with incredible precision. We developed computers powerful enough to analyze vast amounts of data, and suddenly we could see further and more clearly than ever before. We could detect objects from the early universe. We could study their properties. We could understand what they were telling us about cosmic history. J2245+3743 represents the culmination of that technological trajectory. It's the brightest transient ever recorded, yes, but it's also a testament to what we're capable of observing and understanding. We detected something that happened so long ago that the very atoms of which you're composed didn't exist yet. We detected it, analyzed it, understood what caused it, and integrated that understanding into our body of knowledge about how the universe works. That's not just a scientific achievement. That's a human achievement. That's something our species should be genuinely proud of. We went from wondering about the stars to actually understanding them. We went from mythology and superstition to physics and evidence. We went from guessing to knowing. That's a progression that took thousands of years. But we got here, and now the question is, what do we do with that knowledge? Because that's the real question facing humanity now. We have the knowledge, we have the understanding, we have the capability to observe and comprehend the universe at extraordinary levels of detail and precision. But what are we going to do with that? How are we going to use that knowledge? Are we going to continue funding science and exploration? Are we going to continue pushing the boundaries of understanding? Or are we going to let that capability atrophy? History shows us that when societies stop investing in science and exploration, when they turn inward, they tend to decline. Societies that pursued knowledge and understanding and innovation tended to prosper and progress. Societies that became complacent and stopped seeking to understand the world around them tended to stagnate. There's a direct connection between intellectual curiosity and societal progress. So in a sense, the question of whether we continue to pursue discoveries like J2245+3743 is not just about astronomy. It's about the kind of civilization we want to be. It's about whether we value knowledge and understanding. It's about whether we're willing to invest in the future and in expanding human capability. It's about how we see ourselves and our potential. And here's something else that's worth thinking about. Every person who works in science, every astronomer and physicist and engineer, every student studying to enter these fields, they're all driven by curiosity. They're all motivated by the desire to understand. They're all participating in a human tradition that goes back to the beginning of our species. The desire to look at the world and ask why. The desire to understand how things work. That desire is precious. It's fundamental to human nature. It's what makes us explorers and discoverers and innovators. And when we support science, when we fund research, when we celebrate discoveries like J2245+3743, we're nurturing that fundamental human drive. We're saying that curiosity matters. We're saying that understanding is valuable. We're saying that expanding the boundaries of knowledge is worth doing. But science doesn't happen in isolation. It doesn't happen in ivory towers disconnected from society. Science happens because people care about understanding, because communities support the infrastructure needed for research, because governments and institutions make decisions to fund exploration, because parents encourage their children to pursue careers in science, because teachers inspire students with wonder about the natural world. It's a collective effort. It's a societal commitment. And when we see something like J2245+3743, when we learn about a discovery that's been made through the combined effort of scientists and engineers and observers from around the world, it should inspire us. It should make us want to support more science. It should make us want to encourage young people to pursue careers in science. It should make us want to be part of that grand quest for understanding. Because here's the thing that I want to leave you with. Here's the ultimate message that I want to get across. The universe is vast and ancient and filled with phenomena of staggering scale and violence and beauty. And we, despite being infinitesimally small in cosmic terms, have developed the ability to understand it. We can look across 10 billion light years. We can peer back through 10 billion years of time. We can understand the physics of black holes and gravity and the behavior of matter under extreme conditions. We can comprehend things that our ancestors would have thought were impossible to know. That's remarkable. That's genuinely extraordinary. And it's something we should celebrate. It's something we should build on. It's something we should continue to invest in and support. So what I want to ask you, what I want you to think about as you finish watching this is this. What does J2245+3743 mean to you? What does this discovery make you feel? When you consider that astronomers detected an explosion from 10 billion years ago, that we've figured out what caused it, that we've developed the technology to observe something so distant and ancient, what goes through your mind? Does it make you feel small and insignificant? Does it make you feel awed and inspired? Does it change how you think about your place in the universe? Does it make you curious about what else is out there waiting to be discovered? Does it make you want to learn more about astronomy and physics and the cosmos? I'm genuinely curious. I want to hear what you think. So please, if you watched this far, if you've taken the time to journey through this exploration of J2245 plus 3743 and what it means, I want you to comment below. Tell me what you're thinking. Tell me what you're feeling. Tell me what questions you have. Tell me if this changed your perspective on anything. Tell me if you want to learn more about this topic or related topics. And here's the thing. I'm not asking for comments just for engagement metrics or algorithm optimization or whatever. I'm asking because I genuinely care what you think. I'm asking because this community, this group of people who are curious about the cosmos and interested in learning about science, that community matters. Your perspectives matter. Your questions matter. Your enthusiasm matters, because that's how science advances, through dialogue, through people asking questions and seeking answers, through the collective effort of curious minds working together. You might have insights or perspectives that I haven't considered. You might have questions that point toward areas worth exploring. You might have experiences or knowledge that can contribute to the broader conversation about science and discovery. So if you haven't already, please subscribe to this channel, because there are more discoveries coming. There are more phenomena to explore. There are more mysteries to investigate. Astronomy is advancing rapidly. Every week there are new findings, new telescopes are coming online, new understanding is being developed, and I want to share that with you. I want to bring those discoveries to your attention. I want to explore what they mean and why they matter. And beyond just subscribing, I want you to think about how you can engage with science and discovery in your own life. Maybe you're interested in getting a telescope and observing the night sky yourself. Maybe you're interested in reading popular science books to learn more about how the universe works. Maybe you're interested in supporting science education or funding for research. Maybe you're interested in pursuing a career in science or engineering. There are many ways to participate in this grand human quest for understanding. Whatever path you choose, I want you to remember this. Remember that we live in an era where humanity has achieved something genuinely remarkable. We can observe the ancient universe. We can understand extreme physics. We can detect phenomena that are so far away and so ancient that they defy intuition. We're capable of extraordinary things when we direct our intelligence and resources toward understanding. And that capability, that achievement, it's something to build on. It's something to celebrate. It's something to be proud of as a species. The next time you look up at the night sky, the next time you see the stars, remember that behind those points of light are incredible phenomena. Behind them are stories of cosmic violence and creation. Behind them are questions waiting to be answered and mysteries waiting to be solved. And we have the capability to seek those answers and solve those mysteries. That's the ultimate message of J2245 plus 3743. That's what makes this discovery so significant. It's not just about one bright explosion. It's about what we've achieved in being able to observe and understand it. It's about the potential we have as a species to comprehend reality at the deepest levels. It's about the future of human knowledge and exploration. So thank you for taking this journey with me. Thank you for spending the time to learn about this discovery. Thank you for thinking about what it means. And most importantly, thank you for being curious. Thank you for caring about understanding the universe, because that curiosity, that drive to understand, that's what's going to carry humanity forward. That's what's going to help us solve the challenges we face. That's what's going to help us build a better future. The universe is waiting. The stars are waiting. The mysteries are waiting. And we're ready to meet that challenge. We're ready to observe. We're ready to question. We're ready to understand. And that's the most exciting thing of all. Comment below and tell me what you think. Subscribe for more cosmic discoveries. Share this with anyone you know who loves space and science. And keep looking up, because the next great discovery might be waiting in the night sky. The next profound truth might be hidden in the light from a distant star. And we, through our collective curiosity and dedication to understanding, we're going to find it. That's a promise. That's a challenge. That's the future of human knowledge and exploration.